I'm going to talk about Chapter 8, which is on number theory. So we're talking about all these concepts: factors, divisibility, multiples, prime numbers, greatest common factor, least common multiple, and number systems. So remember that in 8.1 and 8.2, we studied knowing the meaning of factors and multiples, greatest common factor and least common multiple, and you are to be able to describe activities and problems to teach those concepts to children. In 8.3 and 8.5, we studied an understanding of prime numbers and the significance of prime numbers to the world. Also, we need to understand how to use trial division to determine if a number is prime, and then using divisibility tests was also part of 8.3 and 8.5. And we also talked about even and odd numbers in that section. And then in 8.6 and 8.7, we learned about explaining the number system, and so how complex the system of numbers can be and how confusing that can be for kids. And so we talked about understanding that on a different level, and then also understanding where rational and irrational numbers fit in and why. And then also we talked about proving or understanding why 0.9 repeating is equal to 1. And so that's all the content that I'm going to talk about in this video. So let's get started. First of all, I'm going to talk about factors and multiples. So remember that a factor, factors are numbers that you can multiply together to get another number. So for example, 2 and 3 are factors of 6 because 2 times 3 multiplied together gives us a product of 6. It's also important to note that the word factor can also be used as a verb, as in to factor something, and to factor something means to find the factors of that number. A multiple is the result of multiplying a number by an integer, not a fraction. So the example is that 12 is a multiple of 3 because 3 times 4 is 12. And so also in this section, you had to not just know the meaning of factors and multiples, but also how to describe an activity or write a problem that would help teach that concept to students, to children. And so I'm going to go through a factor problem and a greatest common factor problem, and then I'll do the same thing with multiples and least common multiples. So we'll start with factors. There are 36 students, and there are, in my first section of Math 234. So if I wanted to arrange all 36 of you into equal rows, how could I do that? So what I could do is I could have, or what I'm looking for, I'm looking of course at the factors of 36 so that I can figure out all the different ways of combining the factors to get those equal row arrangements. So I could have 1 row of 36, I could have 2 rows of 18, I could have 3 rows of 12, 4 rows of 9, and then of course 6 rows of 6. But I could also have the reverse factorization of that list. So for example, I could have 36 rows of 1, which would be silly to call those rows, I guess. But I could also have 18 rows of 2, I could have 12 rows of 3, I could have 9 rows of 4. So these tell me all of my possible arrangements because I'm looking at all the possible factors of that number. The greatest common factor problem that I'm going to use is this one with pencils and notebooks. So let's say that I have 100 pencils and I have 75 notebooks. I want to figure out the greatest, so this is the greatest common factor, I want to figure out the greatest number of children that I can give those pencils and notebooks to without having any leftover notebook. And I of course want them to share them equally. So what I'm going to do is I'm going to list all the factors of 100 and all the factors of 75. And when I do that, I can see that I have 3 common factors in 175. I have 1 as a common factor, I have 5 as a common factor, and I have 25 as a common factor. So I'm looking for the greatest number of children that I can share those notebooks and pencils with. So I'm looking for the greatest of those common factors, and that would be 25. Okay, so let's talk about multiples now. Multiples, of course, remember, are the result of multiplying a number by an integer. So in this problem, I'm going to use my daughter Lena, and she is making these magazine paper beads, and they happen to be 4 centimeters in length. And she wants to use those beads to make necklaces for her friends. And so she wants to know how many different necklace lengths are possible. What are all the different lengths of necklaces, assuming that she's putting them bead to bead, end to end? What are the different lengths that are possible? And so of course we know that this is a multiple problem because we're going to figure out how many different sets of 4 together can we get. So I'm going to list all the multiples of 4 here: 4, 8, 12, 16, 20, 24, 28, 32, 36, 40, 44, and of course we can keep going because with our multiples we can just keep going forever. I should have a ... here. Not all of these make sense. a single bead would not make a necklace. 2 beads themselves wouldn't make a necklace. So of course some of these answers don't make sense in the context of the problem. So those are too small of a number for a necklace. And then sometimes you might get into some larger numbers that wouldn't make sense either for a necklace. But the idea is the same, that we're looking at the multiples of 4 to get all of our possibilities. Now let's talk about a least common multiple problem. So in this problem, I'm going to use pencils and notebooks again, but this time I'm going to talk about multiples. So we're going to say that pencils come in packages of 12. So each package has 12 pencils. And we'll say that notebooks come in little bundled packages of 5. And so this time, instead of, like I did over here, wanting to know the largest number, this time I want to know what is the smallest number of pencils and notebooks that I can buy, because I don't want to spend a lot of money. So what's the smallest number that I can buy so that I can distribute them to my students and not have any remainder, and they will get an equal amount. So I'm going to list the multiples of each of these numbers to figure out how to solve this problem. So when I list the multiples of 12, this is what I get: 12, 24, 36, 48, 60, 72, 84, 96, 108, and so on. I'm going to do the same thing with 5, 10, 15, 20, 25, 30, 35, 40, and so on. And when I do, I'm consciously aware of where my multiples line up. And I don't find a common multiple, actually, until I get to 60. And so there's my first common multiple. Well, since it's the first one I come to, then it's also my least common multiple. So I know that 60 has to be part of my answer when I'm coming up with my answer. I wanted to know the smallest number, so back to the question. I wanted to know the smallest number of pencils and notebooks I could buy. And it's not 60 per se, because I know that pencils come in packages of 12. So I need 5 packages of 12. So I need to buy 5 packages of pencils, because 5 times 12 will give me that 60. And then I need 12 packages of notebooks, because they come in packages of 5. And I know that 12 times 5 will give me that 60 as well. Okay. Next, I'm going to talk about prime numbers. And remember, in class, we talked about the significance of prime numbers to the natural world, and I'll address that as well. So just remember that prime numbers have factors of just 1 in themselves, versus composite numbers that have multiple factors. In class, we talked about the cicada life cycle as being a significant phenomena in nature that utilizes prime numbers. And we believe that it's not just by coincidence. We believe that that is an evolutionary tactic that has enabled the cicada to be so successful. Also, cryptography uses prime numbers. So like encrypted algorithms use the whole concept of prime numbers in order to encrypt and sort of scramble codes. So there's lots of real world applications to prime numbers. What we're going to talk about is what makes a number, how can we tell if a number is prime? So pretty much everybody can tell me like the first, say, 10 prime numbers that come to your mind. But if we have some larger numbers, we need some strategies to figure out how we can tell if a number is prime. And so one that we're going to talk about is trial division. What trial division is taking that number and dividing it by prime numbers. So if you'll notice here, these are all the prime numbers that I've listed. So I'm going to divide by 2, and I'm going to divide by 3. And what I'm trying to see is whether it divides that prime number evenly. And if it does, then it's not prime. But if it doesn't, and I'll talk about that as we go. So you can see that it does not divide 2 evenly, it does not divide 3 evenly, or 5, or 7, or 11, or 13, or 17. But I'm going to stop right here. And the reason that I'm going to stop is because I want you to notice what happens to the quotient. So as the prime number that I'm using as the divisor, so these are all prime number divisors, as that prime number divisor increases, the quotient decreases. And here the quotient is still, so please notice that here the quotient is still larger than the divisor. But as I continue, look at how close the quotient and the divisor are getting. And here the quotient is still larger than the divisor when I divide by 13. But suddenly when I divide by 17, now my quotient is smaller than the divisor. And that's significant to me because I know then if I continue this, my next prime number would be 19. If I continue dividing by my next consecutive large prime number, the same thing's going to happen, right? The quotient will still get smaller. And so that just simply tells me that I don't need to keep dividing. I've gone far enough. If it's not evenly divisible by now, by 17, then I know that 283 has to be prime. So it's just a sort of quick, fairly simple way of determining whether a number is prime. I also want to talk about prime factorization. And prime factorization is simply factoring out, if you think of it that way, I guess, a number to its prime factor. So let's look at an easy one like 12. I know the factors of 12 are 1 and 12, and 2 and 6 and 3 and 4. But when I factor this out, notice what happens. I can factor out my 6 into 2 and 3. And so these are now, I'm done. I've factored it to its prime factors. Basically, I know that I've found them all if I get to my prime factors. So we'd say the prime factorization of 12 is 2 times 3 times 2, or 2 squared times 3. Notice all of these, again, are prime factors. I can do the same thing with 147. It's a little larger number. 1 and 47 can factor to 3 and 49, which factors to 7 and 7. And 3 and 7 and 7, 3 times 7 and 7, those are all prime factors. So we'd say the prime factorization of 147 is 3 times 7 squared. Okay, next I'm going to talk about divisibility. And with that, I'll talk about even and odd numbers. So remember in class we talked about how to define even and odd numbers. And so we'll talk about that just briefly first. So first of all, we know that an even number is divisible by 2. We know then that an odd number, when we divide it by 2, will always have a remainder. And it really is as simple as that. If you think about pairing up toothpicks, and you pair up even toothpicks, they'll always be a pair. But if you pair up an odd number of toothpicks, you will always have an extra. You will always have a remainder. So let's talk about what happens when we multiply our even numbers and our odd numbers. Well, if we multiply 2 evens together, then we always get an even product. And why is that the case? So if you look at my blocks here, if I have an even number of groups and I'm multiplying that by an even number in each group, then what's going to happen is they're always going to pair up. So in this case, I have 4 groups of 8. And 4 groups of 8, well, they'll always be pairs. Every one of these will always pair up with another one. So I will never have any remainders. So an even times an even will always be an even for that reason. Sort of the opposite of is true with an odd times an odd. Look what happens with an odd times an odd. If I take an odd number, so there's a remainder here, right? If I pair these up, times another odd number, then there will always be a remainder because I'm looking at taking 3 groups of another odd number. So in this case, 3 groups of 5 will give me 15, and I can pair up those parts, stick those blocks together, but I will always have an extra remainder. An even times an odd and an odd times an even, it's really the same case. What's going to happen is you're going to always have numbers that pair up. Because if you have an even number of groups times an odd number, you still have that even number of groups to pair up those odd number of blocks. And so they'll always pair up with no remainders. And it doesn't matter if you're taking an even number of groups or an odd number of groups. You'll always have that situation, that pairing up situation. Okay, let's just talk about divisibility testing. Divisibility tests are simply just to determine whether a number is divisible by that number. And there are some quick little divisibility tests that I just want to talk about. You can also design divisibility tests with talking about bundling toothpicks or talking about putting blocks together. But these are just some simple divisibility tests. So we all know that if a number is divisible by 2, then we can just look at its last digit. And if the last digit of that number is a 0, 2, 4, 6, or 8, then we know it's divisible by 2. We know a number is divisible by 3 if we sum the digits, add the digits together, and that sum is divisible by 3. We also looked at summing the remainders when you bundle with, say, toothpicks, and if we sum the remainders and the remainder sum is divisible by 3, then we also know that the number is divisible by 3. That one's a little more complicated to wrap our head around or to maybe explain to kids or to model, but it's another divisibility test for 3. The divisibility test for 4 is pretty simple and straightforward. In fact, most of these are. It's just the last 2 digits divisible by 4. Of course, we all know that a number is divisible by 5 if its last digit is a 0 or a 5. A number is divisible by 6 if it's also divisible by 2 and 3. A number is divisible by 8 if the last 3 digits, so this is kind of like 4, if the last 3 digits are divisible by 8, or if it's divisible by 2 and 4. A number is divisible by 9 if the sum of the digits, this is like 3, if the sum of the digits are divisible by 9. And then, of course, we all know that a number is divisible by 10 if its last digit is 0. Okay, and lastly, I want to talk about rational and irrational numbers. And I want to do that in the sense of number systems. So we were talking in class about how students understand what numbers are. And then they get up into higher elementary and we start talking about things like whole numbers and rational numbers and counting numbers and integers, and pretty soon kids start to get confused because they thought they understood what the word numbers meant, and now we're throwing around all these other labels to numbers. So it's helpful to try to explain that. This is a Venn diagram that is in our text. It's also one that we talked about in class, and it just shows us sort of the relationship between our counting numbers, our whole numbers, our integers, our rational numbers, and then over here, all by itself, are our irrational numbers. Those are our numbers like pi, square root of 2, phi. All those numbers belong in their own category. But the way I like to explain this to students is by helping them understand how a number can be an integer that is also a whole number, that's also a counting number. And that's where it gets confusing, because kids want to label numbers as one or the other. And numbers, of course, can be several different categories. And that's what the Venn diagram is trying to show. I'm going to use this bucket analogy to help with that. So the counting numbers are just simply like 1, 2, 3, 4, and so on. I always think of the counting numbers are the numbers that toddlers will use when they start to count. They always start with 1, 2, etc. Our whole numbers are all of our counting numbers. So imagine that this bucket is full of the counting numbers, and we pour that bucket into this bucket. And so the whole numbers, this bucket is full of all those counting numbers plus the addition of 0. And those become now our whole numbers. So there's an example of a number that is a whole number. It's also called a counting number. We do the same thing with our integers. So our whole number bucket gets dumped completely into our integer bucket. So all of these integers that are in here, they're also the whole numbers. They're also the counting numbers. But now we're also including our negative numbers, as you see here in this example. We do the same thing with our rational numbers. We're dumping our entire bucket of integers into here. So we have all of these numbers in here are integers. They're also whole numbers. They're also counting numbers. But now they're also including our decimals and our fractions. And this would also include our terminating as well as our repeating decimals. So a lot of times students think that our repeating decimals are irrational. They are not. If they make sense, if they're repeating, they have a sensible pattern, they're considered rational numbers. Okay, and then the last thing I want to talk about is this idea that really blew everybody's mind, and it really blows a lot of people's minds, and that is that 0.9 repeating is equal to 1. This is another way to write 1. It's another representation. Just like we use 0.5 to represent 1/2 as another way to write 1/2, we can use 0.9 repeating as another way to write 1. That's a new idea for a lot of people, and it really blows people's minds. So I just want to remind you of a few examples that we talked about in class that show that, in fact, this is true. Probably my favorite example is this one. We all know that 1/3 is 0.3 repeating, and we can draw a picture of what that 1/3 looks like. We know that 2/3 is 0.6 repeating, and we can draw a picture of what that 2/3 looks like. And then when we add 1/3 and 2/3, we get 3/3, which we all know to be 1 whole, right? Then when we add 0.3 repeating plus 0.6 repeating, we get 0.9 repeating. So here we're showing that 1 whole is equal to 3/3, and that's equal to 0.9 repeating. And then pictorially, we can represent that as well, showing our 3/3. That's probably my favorite example. Another example I like is just finding this pattern in our ninths, and this is just a pretty slick pattern because we know that 1/9 is 0.1 repeating, and 2/9 is 0.2 repeating, and 3/9 is the same as 1/3, which is 0.3 repeating, 4/9, 5/9, 6/9, 7/9. We have this very predictable pattern. Notice what happens. 8/9 is 0.8 repeating, so 9/9 is 0.9 repeating. But we all know that 9/9 is equal to 1 whole. So there's just another example following that logical numerical pattern. And then we can look at it algebraically. Let's just say that x is equal to 0.9 repeating. And then we're going to multiply both sides by 10. So we end up with 10x is equal to 9.9 repeating. And then if we subtract, we're going to do this to both sides. So we're going to subtract this from both sides. So let's subtract our 0.9 repeating from both sides. And we get 10x minus x. And that'll give us 9x. And then if we subtract 0.9 repeating from 9.9 repeating, of course we're left with 9. So then we're left with 9x equals 9. And if 9x equals 9, then we know x is equal to 1. But we started with x is equal to 0.9 repeating. So the arithmetic here, the algebra here, shows us that, once again, 0.9 repeating is equal to 1. Okay, thanks for listening. I hope this helps as a review, a summary study for the exam. Thanks, everybody.